A colossal giant sleeps deep in the cosmos. Nestled within the Coma Cluster, the galaxy NGC 4889 reigns supreme, a titan holding 50 of the universe's most baffling secrets. By the end of this journey, you will possess a new understanding of how galaxies truly live and die. We will confront a supermassive black hole that defies all logic and unravel the ghostly trails of stars ripped from cannibalized galaxies. What cosmic mystery calls to you the most? At the very heart of this sleeping giant lies a gravitational paradox so immense it challenges our understanding of cosmic monsters. This is the supermassive black hole at the core of NGC 4889, a behemoth whose estimated mass is almost 21 billion times that of our own sun. To even begin to grasp that scale, consider the black hole at the center of our Milky Way, Sagittarius' star. That familiar titan is a mere featherweight in comparison, a tiny fraction of the colossal entity reigning here. A gravitational presence of such magnitude should be the brightest, most violent object in the observable universe. A frenzied quasar blazing with the energy of a trillion stars as it devours everything nearby. Yet it is profoundly, eerily silent. The monster is not feeding. It slumbers in a state of deep dormancy, a cosmic paradox of unimaginable power existing in near total quiet. How does a black hole of such legendary appetite simply stop consuming? This quiet is the real mystery. It suggests a past of unimaginable feasting, a period where it gorged on stars and gas until it reached this staggering size, only to then enter a state of hibernation, having effectively cleared its immediate celestial plate. What could have caused such a dramatic shutdown? Was it a galactic event that stripped away its food source? Or did the beast simply exhaust everything within its reach? The silence of this titan speaks volumes about the violent, turbulent history hidden within this seemingly calm galaxy. This dormant giant is held in an invisible cage of its own making. Surrounding NGC 4889 is a ghostly halo of dark matter, a cosmic scaffold so immense that its gravitational influence is the only reason the galaxy hasn't flown apart. We cannot see this dark matter, we cannot touch it, but we can witness its ghostly hand at work through a cosmic trick called gravitational lensing. As light from more distant galaxies travels through the space around NGC 4889, it doesn't travel in a straight line. The immense, invisible mass of the dark matter halo warps the fabric of space-time itself, bending the light like a lens made of pure gravity. By mapping this distortion, astronomers can weigh the halo and trace its shape. What they found is deeply puzzling. The distribution of this dark matter does not perfectly match the predictions of our best models. It is not a smooth, evenly distributed sphere of invisible mass. Instead, its profile is strange, perhaps lumpy or stretched in unexpected ways. This mismatch is a profound clue. It hints that something is happening within the dense core of the Coma Cluster that we do not yet understand. Perhaps the dark matter particles are interacting with each other in unknown ways. Or maybe the violent gravitational tides from countless galactic mergers have sculpted this halo into a shape that defies our current physics. The silent black hole at the galaxy's heart is a mystery of absence, but this dark matter halo is a mystery of presence, a ghostly fingerprint pointing toward forces we have yet to name. These faint stellar streams are the ghostly scars of a cosmic feast. Wrapping around the colossal galaxy NGC 4889 are vast, faint rivers of stars, flowing in long, graceful arcs. They are the undeniable evidence of galactic cannibalism. the remains of smaller satellite galaxies that were torn apart and consumed by the immense gravity of this titan. This is not a relic of some ancient, forgotten event. These streams are active, dynamic structures, still settling into their new home. They offer us a real-time view of galactic evolution, a slow-motion digestion process that takes billions of years. Imagine a spoonful of cream swirling into a dark coffee. At first, the cream forms distinct tendrils and ribbons, slowly mixing and losing its identity as it becomes one with the beverage. This is precisely what is happening around NGC 4889, but on a scale so vast, it defies human comprehension. The stars from these devoured galaxies are being stretched out. Their orbits were written by the dominant gravity of their captor. By studying the precise shapes and densities of these streams, astronomers can trace them back to their original galactic structures, learning not only what was eaten, but how the meal unfolded. The very presence of these distinct streams, which have not yet fully dissolved into the main galaxy's halo, tells us that the cannibalism is recent in cosmic terms. It reveals a galaxy that is still actively growing, still imposing its will on its smaller neighbors. This is the hidden violence beneath a seemingly calm exterior, a continuous process of construction and destruction that shapes the universe we see today. Orbiting this cannibal giant are its most improbable survivors, a population of ghostly, ultra-diffuse galaxies. These cosmic wraiths are vast in size, often as wide as our own Milky Way, yet they contain only a tiny fraction of its stars, perhaps just 1%. They are so faint and spread out, they are barely visible against the blackness of space, like a puff of smoke held together by the faintest of whispers. Their very existence here is a profound cosmic puzzle. How can something so fragile, so seemingly delicate, survive in the violent gravitational neighborhood of a titan like NGC 4889? The tidal forces unleashed by the central galaxy should have long ago shredded these fluffy structures, tearing them apart into those very stellar streams we just observed. The fact that they endure suggests they are held together by something far stronger than their visible stars alone can account for. The leading theory points to an overwhelming presence of dark matter. These galaxies may be so densely packed with this invisible substance that its gravity creates a potent binding force, a cosmic glue that holds the fragile stellar population together against all odds. It is as if a dandelion seed were made of lead, its fluffy appearance belying an immense inner strength. Their survival forces us to reconsider what a galaxy truly is. Is it defined by its shining stars, or by the unseen, dominant mass that dictates its fate? These ultra-diffuse satellites are living experiments, testing the limits of structure and survival in the most extreme environments the universe has to offer. The galaxy's chaotic history is written in the swarms of ancient stars orbiting its core. NGC 4889 is surrounded by a phenomenal number of globular clusters, dense spheres containing hundreds of thousands of stars each. While our own Milky Way boasts a respectable population of around 150 of these clusters, the count around this cosmic titan soars into the thousands. This staggering abundance is the first major anomaly. A galaxy of its size should have a great many clusters, but the observed number is far beyond what any model predicted. It is an overachiever, a cosmic collector on a scale that defies simple explanation. The second, even stranger clue lies in how these clusters move. Instead of tracing orderly, circular orbits around the galactic center, many follow wildly eccentric, elongated paths. They plunge in extremely close to the galactic core on a terrifyingly fast approach, only to swing back out to the distant reaches of the galaxy's halo. Such chaotic orbits are a clear sign of a violent past. These clusters are not native to NGC 4889. They are stolen treasures, celestial loot ripped from smaller galaxies during those long-ago acts of cannibalism. When a large galaxy merges with a smaller one, the gravitational turmoil is immense. The smaller galaxy is torn apart, its stars stretched into streams, but its dense, tightly bound globular clusters are remarkably resilient. They survive the encounter, but their orbits are completely scrambled, captured by the far stronger gravity of the victor. With each merger, NGC 4889 added not just stars but entire families of these ancient clusters to its collection, creating the rich and disordered system we see today. This chaotic swarm is a permanent record of every major galactic collision, a living archive of conquests written in the motion of a million suns. What other secrets might these captured clusters hold about the galaxy's violent formation? Even the most monstrous cosmic engines eventually run out of fuel. Stretching far beyond the visible stars of NGC 4889 are the faint, ghostly echoes of a past eruption, colossal structures known as radio lobes. These are the ancient remnants of jets that once blasted out from the galaxy's core when its central black hole was an active, feeding beast. These lobes are a fossil record of violence, a snapshot of a frenzy that subsided millions of years ago. They are the final, fading breath of a quasar that has since fallen silent. Their very structure holds clues to the black hole's feeding habits across cosmic time. The shape and size of these lobes reveal the direction and power of those ancient jets, while their faint, diffuse nature tells us the eruption did not end abruptly. It was a slow, sputtering shutdown, like a firework fizzling out after its grand finale. This relic demonstrates a fundamental cycle of galactic life. The black hole feasted, grew to its immense size, and unleashed torrents of energy that heated the surrounding gas in the intracluster medium, the thin soup of matter between galaxies. This act of self-regulation likely pushed potential food sources away, effectively starving the black hole and forcing it into the deep dormancy we witness today. It is a cosmic feedback loop of breathtaking scale, where the monster's own violent outbursts sealed its fate, creating the profound quiet that now puzzles us. What other cycles of feast and famine might be written in the faint radio whispers of other silent giants? Even the galaxy's protective shroud tells a story of violent motion. Encasing NGC 4889 is a vast halo of gas so incredibly hot that it glows not in visible light, but in high-energy X-rays. This atmosphere, with temperatures reaching millions of degrees, should be a chaotic and smoothly blended soup. Yet, when viewed through X-ray telescopes, this seething ocean reveals something impossible: sharp, wave-like edges slicing through the inferno. Astronomers call these structures cold fronts, a name that is deeply misleading, for these edges are still scorchingly hot. They are merely slightly cooler and denser than the surrounding gas, creating a stark boundary as distinct as a weather front in our own sky. These are not gentle ripples. They are the colossal bow waves and wake created as the entire galaxy, with all its billions of stars, plows through the thin intracluster medium of the Coma Cluster at staggering speeds. It is the cosmic equivalent of a ship cutting through water, leaving a turbulent trail behind it. The sheer existence of these sharp fronts is the first mystery. In such a hot, high-pressure environment, you would expect these boundaries to dissipate almost instantly, smeared into a blur by intense heat and supersonic motion. The fact that they remain crisp and well-defined for millions of years defies our basic understanding of how gases behave under extreme conditions. What unseen magnetic fields, or what subtle properties of the plasma itself, are acting as a cosmic preservative, maintaining this impossible structure. This stable chaos is a natural laboratory, testing the laws of fluid dynamics on a scale we could never replicate, forcing us to question if we truly understand how the universe stirs its most immense cauldrons. The galaxy is a cosmic desert, starved of the very material needed to create new life. Deep within NGC 4889, astronomers find a puzzling void, a critical lack of the cold gas and dust clouds that serve as the nursery for newborn stars. This giant should be rich with interstellar fuel, yet it possesses only a faint whisper of this vital material. It has entered a state astronomers call red and dead, its vibrant days of star formation long over, leaving behind a population of aging, redder stars with no new, blue stars to replace them. How does a galaxy of such immense size and power simply run out of gas? The first compelling theory points directly to the sleeping giant at its heart. In its ancient active phase, the supermassive black hole would have been a brilliant quasar, its intense radiation and powerful jets acting like a cosmic hurricane. This phenomenon, known as active galactic nucleus feedback, could have blown the galaxy's reservoir of cold gas clean away, ejecting it into the vast emptiness of intergalactic space. The black hole essentially sterilized its own home, shutting down the very process that could have continued to feed it. Another possibility is far more simple, yet just as final. The galaxy may have simply used up all its fuel in a series of glorious, explosive bursts of star formation in the distant past. It feasted on its gas reserves so efficiently and so completely that it now has nothing left, a cosmic engine that burned through its fuel too quickly. This theory paints a picture of a glorious, violent youth, a period of frantic stellar birth that left behind the rich population of stars we see today, but with no resources for a future generation. Is the galaxy a victim of its own internal monster, or did it simply live too fast too soon? The answer likely lies in a combination of both, a cycle of creation and destruction that ultimately left this titan quiet, red, and eerily still. This supermassive black hole presents a puzzle that goes far beyond its silent slumber. The very size of this cosmic monster appears to break a fundamental rule of galactic architecture, a rule astronomers call the M-sigma relation. This is a universal correlation, a tight and predictable link observed across nearly all galaxies between the mass of the central black hole and the properties of the galaxy's central bulge, the dense swarm of stars at its core. Think of it as a cosmic scaling law, a consistent blueprint where a larger, more massive central bulge always hosts a proportionally larger black hole. It is a fundamental partnership, suggesting that black holes and their host galaxies grow together, their fates intertwined across billions of years. Then there is NGC 4889. Its central black hole, with a mass of 21 billion suns, is not just large, it is disproportionately, overwhelmingly massive. When astronomers place it on the M-sigma graph, it does not sit neatly on the line with other galaxies. It resides in a realm all its own, a glaring outlier that challenges the very foundations of this rule. How could a black hole grow so much more massive than its galactic home should allow? The answer may lie in the galaxy's violent history of cannibalism. Each time NGC 4889 consumed another galaxy, it did not just add stars to its outer halo. It also funneled vast amounts of gas and stars directly toward its core, feeding the central black hole in a series of colossal feasts. This process may have supercharged the black hole's growth, allowing it to balloon in size far beyond what would be expected from the steady, internal evolution of its original bulge. Alternatively, the galaxy's bulge itself may have been stripped away or puffed up over time by countless gravitational interactions within the dense Coma Cluster, leaving the black hole as a relic of a past, more massive structure. The overmassive black hole of NGC 4889 is not just a curiosity, it is a cosmic warning, forcing us to reconsider how the very largest black holes in the universe co-evolve with their hosts in the most extreme environments. Perhaps the standard rules of galactic growth do not apply in the chaotic, crowded core of a galaxy cluster, where feasting is the primary way of life. This faint, pervasive glow is the ghost of galaxies long dead. Throughout the immense volume of the Coma Cluster, not all light is bound within the distinct disks and halos of its galaxies. A vast, diffuse sea of stars drifts freely in the emptiness between them, a phenomenon astronomers call intracluster light. It is the combined shine of countless billions of orphan stars, a cosmic metropolis of lost souls with no galactic home to call their own. To understand how such a thing is possible, picture a bustling city square during a festival. The people are like stars within a stable galaxy, all moving together in an organized system. Now imagine a sudden, chaotic stampede. In the turmoil, individuals are ripped from the crowd, sent tumbling into the side streets and alleyways, no longer part of any group. On a galactic scale, this is precisely what happens during the violent gravitational encounters between galaxies. As giant galaxies like NGC 4889 cannibalize their smaller neighbors, they do not cleanly absorb every star. The immense tidal forces, the same ones that pull galaxies into streams, also act like a gravitational slingshot, flinging countless stars out into the intergalactic void. These stars become permanent nomads, destined to wander the dark spaces between galaxies forever. The specific patterns of this light around NGC 4889 are a forensic map of its past assaults. The distribution is not smooth and even, but shows faint, swirling structures and asymmetrical plumes. These are the echoes of specific merger events, the final, fading testimony of galaxies that were utterly dismantled. By tracing the subtle contours of this ghostly glow, astronomers can reconstruct a timeline of violence, identifying not just how many galaxies were consumed, but the specific angles and forces of each collision. This intracluster light is more than just a relic. It is a dynamic component of the cluster itself, containing a significant portion of its total starlight. It reveals that the true extent of a giant like NGC 4889 is not defined by its visible edge, but by the vast graveyard of stars it has created around itself. What does it mean for a star to live its entire life in absolute isolation, far from the nurturing cradle of any galaxy? From the wreckage of ancient collisions, new galaxies may be struggling to be born. Among the faint stellar streams and vast plumes of orphan stars surrounding NGC 4889, astronomers have identified dense, compact knots of gas and stars. These are tidal dwarf galaxy candidates, potential infant galaxies forming from the debris of their destroyed parents. It is a cosmic story of rebirth from ruin, where the very material torn apart by the giant galaxy's gravity is now clumping together to create something entirely new. The evidence lies in their motion and composition. These knots are not just random clumps. They are moving with a shared velocity, a clear sign they are gravitationally bound objects, not merely a chance alignment of stars. Spectroscopic analysis reveals they are rich in the cold gas needed for star formation, a stark contrast to the gas-starved giant they orbit. This suggests they are not just remnants, but active, self-gravitating systems capable of creating their own stellar populations. This discovery sparks a fierce debate. Can such a fragile structure truly survive and mature in the gravitational turmoil near a cannibal galaxy? The environment is brutally hostile. The immense tidal forces from NGC 4889 constantly threaten to pull these infant galaxies apart before they can fully condense. Furthermore, the high-speed interactions within the dense Coma Cluster could tear them to shreds in a cosmic instant. Their potential survival challenges our understanding of galaxy formation. We have long believed that large galaxies form from the bottom up, with small galaxies merging to form larger ones. But if tidal dwarf galaxies can form and persist, it suggests a parallel path, a top-down process where large galaxies can actually spawn new, smaller ones from their own discarded material. Are we witnessing the creation of a new galactic dynasty, or merely the fleeting, beautiful illusion of structure in a field of destruction? The fate of these cosmic orphans will tell us if creation can truly persist in the shadow of a titan. This hot halo of gas is not a perfect, symmetrical shroud. When viewed through the sensitive eyes of an X-ray telescope, the atmosphere around NGC 4889 reveals a distinct lopsidedness, a puzzling asymmetry where one side glows far brighter and stretches out much further into space than the other. It is as if the galaxy is wearing its atmosphere like a cloak blown back by a fierce wind. The primary force behind this distortion is a brutal process known as ram pressure stripping. NGC 4889 is not floating serenely in the cluster. It is hurtling through the thin, hot soup of the intracluster medium at several million miles per hour. As it moves, this external gas exerts a tremendous pressure on the galaxy's own atmosphere, much like a powerful gale pressing against your body if you were to lean out of a speeding car. This cosmic wind is literally peeling the galaxy's gas away, piling it up on the leading side to create a brighter, compressed rim, while stretching it into a long, faint tail on the trailing side. The basic concept is straightforward, but the devil is in the details. The precise shape and sharpness of this lopsided halo present a complex hydrodynamic puzzle that simple models struggle to replicate. Why is the boundary between the stripped gas and the galaxy so sharp in some places and fuzzy in others? The extreme temperatures and the galaxy's immense velocity should create chaotic, turbulent flows that smear the boundary into a blur. Yet, parts of it remain incredibly crisp. This suggests that other, more subtle forces are at work, perhaps invisible magnetic fields threading through the plasma, acting like a cosmic scaffold to contain and shape the gas. The exact density and composition of the gas being stripped also factor into this cosmic equation, creating a unique and intricate fingerprint of pressure and resistance. This lopsided halo is more than just a sign of motion. It is a dynamic snapshot of a galaxy fighting to hold onto its own atmosphere against the relentless pressure of its environment. Each subtle contour in its X-ray glow is a piece of a puzzle, challenging us to understand the intricate physics of matter moving at unimaginable speeds through the most extreme of conditions. Scattered like brilliant diamonds against the galaxy's dark canvas are objects of impossible brightness. These are the ultra-luminous X-ray sources, or ULCs, and they shine with the power of millions of suns, yet they are mere pinpricks of light, distinct from the slumbering giant at the galaxy's core. Each one is likely a binary system, a cosmic dance between a normal star and a voracious stellar remnant, either a neutron star or a stellar mass black hole. In these systems, the dense remnant's immense gravity pulls gas from its companion star, forming a swirling disk of superheated material known as an accretion disk. As this gas spirals inward, it is compressed and heated to temperatures of millions of degrees, releasing a torrent of high-energy X-rays. The sheer intensity of this light is the central mystery. For decades, astronomers have operated under a fundamental rule called the Eddington limit. This is the theoretical maximum brightness an object can achieve from accretion, a point where the outward pressure from the radiation it produces perfectly balances the inward pull of its own gravity. Push past this limit, and the radiation should blow the incoming gas away, shutting off the fuel supply and dimming the object. Yet these ULXs in NGC 4889 blast through this limit with ease, shining dozens, even hundreds of times brighter than the Eddington limit should allow. It is like a single candle somehow outshining a stadium's floodlights. How is this possible? The answer may lie in the geometry of the accretion process itself. Perhaps the material is not falling in evenly from all directions, but is being funneled onto the magnetic poles of a neutron star in incredibly focused columns, allowing the radiation to escape through the sides without disrupting the inflow. For black holes, the solution might be that the accretion disk is puffed up and thick, creating a funnel that directs the intense radiation into narrow beams. If one of those beams happens to be pointed directly at Earth, the source would appear far brighter to us than it truly is across all directions. These cosmic lighthouses challenge the very foundations of how matter behaves under the most extreme gravitational stress, forcing us to rewrite the rules of accretion physics. What other fundamental laws might be bent within the intense environment of this cannibal galaxy? A profound quiet hangs over this sea of ancient stars. Given the sheer number of aging suns within NGC 4889, you would expect the occasional spectacular death, a supernova flare briefly outshining its entire galaxy. Yet modern astronomy has recorded none. This absence is deeply puzzling. The galaxy is rich with stellar remnants like white dwarfs and neutron stars, the very objects that should be triggering these cataclysmic explosions. So where are the fireworks? One possibility is that we are simply unlucky. Supernova are rare events in any single galaxy, perhaps occurring only once or twice a century. Our observational records are a mere blink in cosmic time, so it is entirely possible that we have missed a recent eruption simply by not looking at the right moment. But the silence feels more significant than mere chance. It suggests the galaxy is in a uniquely stable and perhaps terminal phase of stellar evolution. The most common type of supernova, the kind stemming from the explosive death of a massive star, requires a youthful, short-lived stellar population. The lack of these events confirms that NGC 4889 has not formed such stars for a very long time. Its star-forming fuel was exhausted eons ago. The other primary type, a thermonuclear supernova, occurs when a white dwarf steals enough material from a companion star to cross a critical mass threshold. The absence of these explosions hints at something even stranger. Perhaps the binary star systems in this galaxy have evolved in an unusual way. The violent gravitational tides from the galaxy's core or from its past mergers may have disrupted these delicate stellar partnerships, preventing the slow accretion of mass that leads to a detonation. We could be looking at a stellar population that has grown old together, a society of suns that has moved past its turbulent, explosive youth into a prolonged and eerily silent retirement. This supernova drought forces us to ask if a galaxy can become too old, too stable for stellar fireworks. Is the profound quiet we observe a sign of a cosmic graveyard settling into its final, permanent form? The very colors of the captured star clusters tell a story of two distinct pasts. As astronomers studied the thousands of globular clusters swarming around NGC 4889, they noticed a peculiar pattern. These dense spheres of stars are not a uniform collection, but instead split cleanly into two distinct families based on their color. One group shines with a distinct reddish hue, while the other glows with a cooler, bluer light. This is the phenomenon of color bimodality, and it is far more than a simple aesthetic difference. The color of a star cluster is a direct indicator of its chemical composition, specifically the abundance of elements heavier than hydrogen and helium, which astronomers call metals. The blue clusters are metal poor, meaning they are composed of ancient, pristine stars formed from the primordial gas of the early universe. The red clusters, in contrast, are metal-rich, containing stars that were forged from gas already enriched with the heavy elements spewed out by previous generations of supernovae. This stark division is a cosmic fingerprint, an indelible record of the galaxy's violent assembly. The blue, metal-poor clusters are the original inhabitants, the native population that formed with the very first version of NGC 4889 itself, or were stolen from other small, ancient galaxies that were among its first victims. The red, metal-rich clusters, however, tell a different tale. They were likely the central clusters of larger, more massive galaxies that were later consumed. When a large, mature galaxy is cannibalized, it contributes its own family of globular clusters, which formed later in cosmic history from gas that had been repeatedly cycled through stars, becoming steadily richer in metals. Each major merger event added a new wave of these red clusters to the mix, while the original blue population continued to grow from the accretion of small, primitive galaxies. The two colors are not blended. They remain as separate today as they were billions of years ago, a permanent testament to the different origins of the stars that now share a single galactic home. This color-coded history book allows astronomers to not only count the mergers, but to classify them, distinguishing between the consumption of many small dwarfs and the monumental collisions with a few large galactic peers. What other chapters of this violent history are written in the simple, silent colors of a million captured suns? The silent giant at the heart of NGC 4889 may be still, but its past resonates across the cosmos. Every time this galaxy consumed another, it did more than just add stars to its halo. With each galactic merger, its central supermassive black hole would have encountered the black hole at the core of its victim. These cosmic monsters spiraled toward one another in a final, violent dance, sending powerful ripples through the very fabric of space-time itself. These ripples are gravitational waves, and the cumulative effect of countless such mergers across the universe creates a faint, persistent hum known as the stochastic gravitational wave background. It is a chorus of ancient collisions, a low-frequency vibration that fills the entire cosmos. Because of its exceptionally violent history of cannibalism, NGC 4889 stands as a prime suspect, a major contributor to this universal soundtrack. Its life of constant consumption means its black hole has likely merged with dozens of others over billions of years. Each merger would have been a monumental event, releasing more energy than all the stars in the observable universe combined, all channeled into these invisible waves. By studying the detailed merger history of this galaxy, by counting the stellar streams and the captured globular clusters, astronomers can essentially count the number of major black hole mergers it has experienced. This allows them to build a predictive model, estimating just how loud its specific contribution to this cosmic hum should be. It is a form of cosmic archaeology, where the ghosts of past collisions are used to tune our instruments to the faintest whispers of the universe. Current observatories cannot yet detect this specific low-frequency hum, but future space-based detectors are being designed to listen for it. When they finally turn on, the signal from giants like NGC 4889 will be a key part of the chorus they hear. This transforms the galaxy from a silent, static image into a dynamic, ringing bell, its past violence still echoing across the void. Deep within the galactic core, the expected cosmic order breaks down entirely. Observations of the stars closest to the center of NGC 4889 reveal a scene of gravitational chaos. Instead of tracing the predictable, elliptical orbits that planets follow around our sun, these stars move in what appears to be a frantic, random dance. They plunge in at steep angles, loop around in tightly wound spirals, and swing past the central void on wildly unpredictable paths. This stellar pandemonium is the direct gravitational signature of the slumbering supermassive black hole. Its 21 billion solar mass presence warps the space around it so profoundly that it acts like a cosmic blender, violently scrambling the orbits of any star that dares to venture too close. The sheer randomness suggests something beyond the black hole's simple, overpowering pull. It hints at a complex and unseen substructure within the core. Astronomers suspect the gravitational turmoil from countless merged galaxies has left behind a hidden population of smaller black holes, dense stellar remnants, and dark matter clumps. This invisible wreckage, all orbiting the central monster, creates a constantly shifting gravitational landscape. A star is not just pulled by one giant mass, but is constantly jostled and tweaked by countless smaller, unseen forces. It is like trying to walk a straight line across a dance floor crowded with unseen dancers, constantly being bumped in new and unexpected directions. This chaotic motion is more than just a spectacle. It is a vital clue. By meticulously mapping these seemingly random stellar paths, scientists can perform a form of gravitational forensics, working backward to deduce the amount and distribution of the invisible mass causing the turmoil. The dance of these stars is a direct probe into the hidden architecture of the most extreme gravitational environment imaginable, a place where the universe's most fundamental force is laid bare in all its beautiful, terrifying complexity. What other invisible structures might be revealed in the frantic steps of this stellar ballet? These ghostly cavities are the lingering breath of the monster. Etched into the scorching X-ray atmosphere of NGC 4889 are two vast, bubble-like voids, colossal regions of emptiness that appear as dark shadows against the brilliant glow of the hot gas. They are not true voids, of course, but regions of far less dense, cooler gas, inflated by the powerful jets that once erupted from the central black hole during its active quasar phase. These are fossil radio bubbles, and they function like cosmic archaeology, preserving the shape and intensity of those ancient outbursts for millions of years after the jets themselves have faded into silence. The process of their formation is a story of immense power. As the black hole fed, it channeled some of the accreting material into two opposing relativistic jets that drilled through the galaxy's gaseous halo. These jets acted like cosmic blowtorches, heating the surrounding gas and pushing it aside to create immense, buoyant bubbles that then rose slowly through the atmosphere, much like a massive air bubble rising through water. Their continued existence is a testament to the stability of this galactic environment. You might expect such structures to dissipate quickly, collapsing under the immense external pressure or being shredded by turbulence. Yet they remain intact, their edges remarkably sharp. This suggests the bubbles are supported by something internal, perhaps a magnetic field or a persistent source of relativistic particles, acting like an invisible scaffold that maintains their shape against all odds. By measuring their size and distance from the galactic center, astronomers can essentially carbon date these eruptions. The further a bubble has risen, the older the outburst that created it. This allows us to piece together a timeline of the black hole's past activity, revealing that it did not shut down in a single event, but experienced multiple, powerful bursts of energy separated by long periods of quiet. These fossil structures are the final, fading evidence of the feedback cycle that ultimately strangled the galaxy, a permanent reminder of the fury that once raged at its heart before the long sleep began. What other ancient eruptions might be hidden within the faintest whispers of this ghostly halo? The galaxy holds a secret in the faint, glowing halos of its dying stars. Scattered throughout NGC 4889 is a specific population of planetary nebulae, the beautiful, ephemeral shells of gas cast off by sun-like stars in their final throes. When a star of modest mass nears the end of its life, it pulsates and expels its outer layers into space, creating a glowing bubble of ionized gas illuminated by the intense ultraviolet light from the hot stellar core left behind. In most giant elliptical galaxies, these objects are reliable cosmic census takers. Because they mark the death of a very specific type of star, their numbers and distribution should give astronomers a precise headcount of the older stellar population, telling us exactly how many such stars live and die within the galaxy. Yet here, the numbers do not add up. The theoretical models, built from observations of other, quieter elliptical galaxies, predict a certain abundance of these glowing shells. But in NGC 4889, that predicted number is off. There are either too many or too few of these nebulae, creating a statistical anomaly that points to a deeper mystery. This is not a simple counting error. It is a sign that the stellar population itself is not what we expected. The anomaly suggests that the galaxy's violent history of cannibalism has left it with a strange mix of stars. Perhaps the process of ripping apart and assimilating so many smaller galaxies injected a surplus of stars into the precise mass range that produces planetary nebulae. Or conversely, the same gravitational turmoil that scrambled globular cluster orbits may have prematurely disrupted the delicate stellar systems that would have created them, leading to a surprising deficit. The chemical fingerprints of these nebulae add another layer of intrigue. By analyzing their light, astronomers can read the composition of the expelled gas, which tells a story about the star that created it. In a normal, isolated galaxy, you would expect a certain consistency in these chemical signatures, but the nebulae in this cannibal giant show a bewildering variety, with some shells being remarkably rich in heavy elements while others are pristine and metal poor. This diversity is a direct echo of the galaxy's chaotic assembly. Each anomalous nebula is a fossil from a different consumed galaxy, a dying star that formed long ago in a separate stellar system with its own unique chemical history. Their presence here glowing with foreign compositions, is permanent proof of the galactic conquests that built this titan. Why does the final breath of these stars not conform to the standard model? The answer is written in the complex and violent biography of the galaxy itself, a history so tumultuous that it has altered the very demographics of stellar death. Some stars within this ancient galaxy are not content to simply orbit in its halo. They are stellar runaways, flung through the void at speeds so immense they threaten to escape the galaxy's gravitational grasp forever. These are the high-velocity stars, cosmic projectiles whose frantic motion tells a story of violent encounters near the most powerful object in the galaxy. The primary suspect for their origin is the supermassive black hole itself. Picture a binary star system, two stars locked in a mutual orbit, drifting too close to the central monster. The black hole's immense gravity can violently tear this partnership apart. It captures one star, pulling it into a tight orbit, while flinging the other away at a tremendous speed, like a gravitational slingshot. This ejected star becomes a hypervelocity traveler, shot out on a one-way trip into intergalactic space. But the black hole is not the only culprit. The galaxy's long history of cannibalism provides another, more diffuse engine for this stellar expulsion. When a small dwarf galaxy is torn apart by the tidal forces of NGC 4889, the stars that once belonged to it are not all neatly absorbed. Just as the encounter can send some stars into new orbits around the giant, it can also impart enough kinetic energy to others to send them flying away as free agents. These stars become the survivors of a galactic wreck, set adrift with the velocity of the catastrophic collision that destroyed their original home. This creates two distinct populations of runaways. The first are the black hole ejectees, stars flung from the very center on precise radial trajectories. The second are the tidal debris ejectees, stars scattered in all directions from the messy sites of galactic mergers. Their ultimate fate is a lonely one. If their speed exceeds the galaxy's escape velocity, they will leave the cluster entirely, destined to spend eternity wandering the cold, dark vastness between galaxies. If they are just a bit slower, they may become part of the intracluster light, forever bound to the cluster's gravity, but never again belonging to a specific galaxy. These high-velocity stars are more than just celestial curiosities. They are direct probes of the most extreme gravitational events. By tracing their paths backward, astronomers can pinpoint the location of past disruptions, almost like following the trail of debris back to a car crash. The very existence of these stellar runaways confirms that the galaxy's calm appearance is a facade, hiding a core of relentless gravitational turmoil. What other secrets of the central black hole might be revealed by studying the trajectories of these escaping suns? A strange, invisible glow surrounds this ancient galaxy, radiating a warmth our eyes can never see. Peering into the infrared spectrum, astronomers have mapped the heat signature of NGC 4889, expecting to find the familiar warmth of interstellar dust grains gently heated by starlight. Instead, they found a puzzle. Specific wavelengths of infrared light shine far more brightly than any known dust or stellar process can account for. This unidentified infrared emission hangs over the galaxy like a ghostly thermal shroud, and its source remains one of its most enduring mysteries. The leading suspect is a complex family of organic molecules known as polycyclic aromatic hydrocarbons, or PA. Imagine these as tiny, flat flakes, miniature snowflake-like structures made of carbon and hydrogen atoms arranged in rings. They are common in space, often found in regions where new stars are forming, and when ultraviolet light strikes them, they vibrate and emit a very distinct set of infrared fingerprints. The problem is, NGC 4889 is a red and dead galaxy, a place with virtually no young stars to produce the harsh ultraviolet radiation needed to make these PHs light up. So if these molecules are the culprits, how are they being excited? Could there be a faint, hidden population of young stars we have not yet detected? Or are the existing, older stars somehow managing to energize these particles in a way we do not understand? Another compelling theory points not to molecules, but to an entirely different form of dust. This would be a population of exceptionally cold dust grains, frigid structures only a few degrees above absolute zero. At such profoundly low temperatures, they would emit almost all their radiation in the far infrared and submillimeter wavelengths, a part of the spectrum that is incredibly difficult to observe with our current telescopes. This dust would be virtually invisible, a cold shadow within the galaxy, and its faint emission could be blending with and amplifying the other infrared signals we detect. The existence of such cold dust would itself be a major puzzle. How could it remain so cold in a galaxy enveloped by a multimillion-degree X-ray atmosphere? It would require dense, shielded pockets where the hot intracluster gas cannot penetrate, like icy caves hidden deep within a scorching desert. Unraveling this infrared mystery is more than an academic exercise. These unidentified emissions are a potential window into the galaxy's hidden chemical complexity. If they are from PHs, it means that the basic building blocks of organic chemistry are not only present but abundant in this supposedly dead system, suggesting a richer interstellar environment than we ever imagined. If they are from cold dust, it forces us to reconsider the true structure of the galactic interior, revealing pockets of material that have somehow survived the galaxy's violent history completely untouched and undisturbed. What other secrets are hidden within this faint, warm glow, just beyond the edge of our current understanding? The chemical map of this giant galaxy reveals a hidden patchwork of foreign territories. As astronomers measure the metal content, the abundance of elements heavier than hydrogen and helium, in stars across NGC 4889, they find a startling lack of uniformity. This is the phenomenon of anisotropic metal distribution, a complex pattern where different regions of the galaxy possess stars with wildly different chemical signatures. In a galaxy that formed from a single, collapsing cloud of gas, you would expect a smooth and gradual gradient, with stars in the dense core being metal-rich and stars in the outer halo being metal-poor. But this galaxy is no such simple object. Its map is a chaotic mosaic, a jigsaw puzzle where each piece tells a different story of origin. A cluster of stars in one part of the halo might be incredibly rich in iron and silicon, while another cluster, just as close to the center, is composed of primordial, metal-poor stars. This unevenness is the direct chemical fingerprint of its cannibalistic past. Each patch of metal-rich stars represents the core of a large, mature galaxy that was consumed. These galaxies had long, busy lives, forging heavy elements in successive generations of stars before they were torn apart. When they merged with NGC 4889, they donated their entire population of chemically enriched stars, planting them like a foreign colony within the larger halo. Conversely, the patches of metal-poor stars are the remnants of small, primitive dwarf galaxies. These galactic infants were consumed before their stars could significantly enrich the gas with heavy elements, so they contributed a population of pristine, ancient suns. The galaxy was not built all at once, but in a series of separate, distinct mergers, each one adding a new piece with its own unique chemical identity. The gravitational turmoil of these collisions was not violent enough to completely homogenize this stellar soup. The different populations were stirred, but not blended, leaving behind a permanent chemical record of every major meal. Why does this matter? Because it allows astronomers to perform a form of galactic genealogy. By reading these chemical tags, they can identify which stars are native to the original galaxy and which are immigrants from specific, now vanished galactic systems. It transforms the seemingly smooth glow of the giant elliptical into a detailed historical archive, written in the silent language of elemental abundance. What other lost galaxies might be hiding in plain sight, their identities preserved only in the unique chemistry of their captured suns. Even the invisible dark matter scaffolding of this galaxy presents a profound contradiction. At the very heart of NGC 4889, where the supermassive black hole warps space and stars dance in chaos, our theories predict the dark matter should be densely packed, rising to a sharp, concentrated peak. Cosmologists call this a cuspy profile, a steeply rising density gradient toward the center, a natural consequence of how dark matter should behave under its own gravity. Yet the observations tell a different story. The data from the motions of stars and the effects of gravitational lensing often point toward a flatter, more gentle distribution in the inner regions, a so-called core. It is as if someone has taken a needle-sharp mountain peak and sanded down its tip into a soft, rounded hill. This core cusp problem is not unique to this galaxy, but here, in this titan born from countless mergers, the discrepancy is thrown into stark relief. How could the most dominant form of mass in the universe fail to clump at the center as our most fundamental models insist it must? The implications ripple outward, challenging the very nature of dark matter itself. One compelling possibility is that dark matter is not the simple, cold, and non-interacting substance we have long assumed. Perhaps dark matter particles can interact with each other through some unknown force, a kind of dark version of electromagnetism. These self-interactions would allow the particles to collide and bounce off one another in the crowded galactic core, transferring energy and effectively smoothing out the dense cusp into a gentler core, much like shaking a bag of marbles will level its surface. Another, more exotic idea is that dark matter possesses a quantum pressure, a faint but pervasive resistance to being squeezed too tightly. If dark matter were ultralight, behaving more like a wave than a discrete particle on galactic scales, this inherent waviness would prevent it from collapsing into an infinitely sharp point, naturally creating the soft cores we observe. The violent merger history of NGC 4889 adds another layer to this puzzle. The immense gravitational forces from its past cannibalism could have physically stirred up the dark matter halo, scrambling the central cusp and leaving behind a mixed and flattened core. Each of these theories points toward a universe far more complex than we imagined, where the dominant substance is not a simple, passive ghost, but an active participant with its own rich and hidden physics. The silent core of this giant galaxy may be holding the key to understanding the true character of the cosmos's greatest mystery. Occasional, brilliant flares may briefly illuminate the black hole's dormant table. These violent flashes are the suspected signatures of tidal disruption events, the moments when a star wanders too close to the supermassive black hole and is torn apart by its overwhelming gravity. The process is one of the most extreme in the universe. As the star is captured, the black hole's tidal forces, the difference in gravity between the side of the star closest to the monster and the side farthest away stretch the star horizontally while compressing it vertically. It is a process called spaghettification, where the star is pulled into a long, thin strand of superheated plasma. This material doesn't just vanish. It forms a swirling, chaotic accretion disk around the black hole. And as the stellar debris collides and compresses, it heats to temperatures of hundreds of thousands of degrees, unleashing a tremendous flare of radiation that can outshine the galaxy's entire stellar population for months. Spotting these specific flares from a galaxy as distant as NGC 4889 is a monumental challenge. The event must be extraordinarily bright to be visible across such a vast intergalactic distance, and our telescopes must be looking in the right place at precisely the right time. Furthermore, we are often seeing the event as it happened hundreds of millions of years ago, a flash from the deep past that we interpret as a current phenomenon. The main obstacle is distinguishing a true tidal disruption event from other brilliant but more common cosmic outbursts, like a supernova in the galaxy's foreground or a flare from a distant gamma-ray burst. Confirmation requires meticulous analysis of the light's specific signature, how its color and intensity change over time, to match the unique profile of a star being devoured. A confirmed tidal disruption event here would be a scientific goldmine. It would provide a direct, real-time measurement of the black hole's properties, allowing us to test our theories about its mass and spin with unprecedented accuracy. The event would also illuminate the immediate environment around the beast, revealing the density and dynamics of the stars in its immediate vicinity. Each flare is a brief, terrifying lighthouse, illuminating the shore of a dark continent for one brilliant moment before the long night returns. This giant galaxy is not an island drifting in random solitude. NGC 4889 is perfectly aligned, its long axis pointing directly along one of the immense, invisible filaments of the cosmic web that structures the entire Coma Cluster. Picture the universe on its largest scales not as empty blackness, but as a colossal spiderweb, with galaxies strung along its glowing strands like dewdrops. These filaments are the highways of the cosmos, conduits of dark matter and diffuse gas that feed the growth of the largest structures. The fact that this galactic titan is oriented along this cosmic flow is far from a coincidence. It suggests that the very forces which built the universe also dictated the final form of this giant. This alignment has profoundly shaped the galaxy's entire existence, acting like a cosmic guide rail for its growth. Throughout its long history, fresh gas from the intergalactic medium would have flowed most efficiently into the galaxy along this filamentary highway, funneling directly toward its core and providing fuel for both star formation and the supermassive black hole. This structured inflow could explain the periods of furious activity in its past, the massive bursts of star formation, and the powerful quasar jets that once erupted from its center. Those jets themselves were likely shaped by this cosmic architecture. Instead of firing in a random direction, the explosive outflows from its active galactic nucleus were probably channeled, constrained by the same dense filamentary environment that fed the beast. This creates a dynamic cycle of construction and regulation, where the cosmic web feeds the galaxy, and the galaxy's subsequent outbursts then heat and disrupt the web around it. The alignment is a permanent clue, a fossilized imprint of the galaxy's preferred direction of growth across billions of years. Why does this specific orientation persist, even after so many violent mergers that should have randomized its spin? It reveals that the large-scale pull of the cosmic web is a dominant force, a gravitational tide so immense that it can orchestrate the final resting position of a celestial titan, ensuring that even in its quiet old age, it still points toward the hidden rivers that gave it life. What other universal patterns might be written into the alignment of this sleeping giant? A faint, all-encompassing whisper of radio waves envelops the entire region around NGC 4889. This is the low-frequency radio halo, a sea of invisible energy so vast it dwarfs the galaxy itself, stretching across millions of light years of the Coma Cluster. It is not a sharp, focused signal like the fossil jets from the central black hole, but a diffuse, almost imperceptible glow that permeates the space between galaxies. This radio whisper is generated by a vast population of relativistic electrons, particles spiraling at nearly the speed of light through the cluster's tangled magnetic fields. As these electrons are forced into curved paths by the magnetism, they release energy in the form of synchrotron radiation, the same process that creates the glow in a laboratory particle accelerator, but on a truly cosmic scale. The sheer size of this phenomenon presents a fundamental puzzle. How does the cluster manage to accelerate these electrons to such incredible speeds across such an immense volume? They are not coming from a single point source like the central black hole. The electrons must be reaccelerated somehow, given a fresh push of energy as they travel through the intergalactic medium. The leading theory points to the colossal turbulence generated by the cluster's own violent formation. As countless galaxies merged and fell into the cluster's gravitational well over billions of years, they created immense shock waves and chaotic flows within the hot, thin plasma filling the space between them. These cosmic shock waves, rippling through the intracluster medium, could act like natural particle accelerators, giving the electrons the boost they need to emit the radio glow we detect. Yet, the exact mechanics remain one of the great unsolved problems in astrophysics. Is the turbulence from ancient mergers sufficient to power this halo? Or are we missing a key piece of the puzzle, perhaps a more subtle and continuous source of energy? This faint radio sea is a direct window into the energetic heart of the entire cluster, a reminder that even in the seeming quiet between galaxies, particles are dancing at the edge of physics, driven by forces we are only beginning to comprehend. The satellite galaxies surrounding this giant are not all receding in an orderly cosmic retreat. A careful census reveals a puzzling deviation, a subtle but significant anomaly in their redshift. Redshift is the cornerstone of modern cosmology, the stretching of light from distant objects as the universe expands, allowing us to measure their velocity and distance through Hubble's law. For most galaxies, this relationship holds true, their redshift cleanly indicating their flight from us. But some of the satellites around NGC 4889 display a small yet undeniable discrepancy. Their measured redshift is slightly off from what Hubble's law predicts for their presumed distance, implying they possess a peculiar velocity of their own, a local motion superimposed on the grand flow of cosmic expansion. This is the faint signature of an unseen gravitational struggle. One compelling explanation points to the immense and complex gravitational field of the central galaxy itself. These satellites are not simply floating in empty space. They are swimming through the deep gravitational well of the Titan and its massive dark matter halo. Their orbits are constantly being tweaked and perturbed, accelerated or decelerated by the invisible tug of this vast concentration of mass. Their anomalous motion could be a simple reflection of this ongoing celestial dance, a temporary swing in their long orbital path. But a more profound possibility exists, a phenomenon known as dynamical friction. Imagine a satellite galaxy moving through the diffuse halo of stars and dark matter that surrounds the central giant. As it travels, its gravity attracts and pulls this background material, creating a slight, dense wake behind it, like the trailing bow wave of a ship. This wake, in turn, exerts a gravitational pullback on the satellite, acting as a subtle brake that steadily saps its orbital energy. This is dynamical friction, a cosmic drag force operating on a galactic scale. Over billions of years, this relentless braking can cause a satellite's orbit to decay, slowly spiraling it inward toward eventual consumption. The anomalous redshifts we see today could be the direct measurement of this process in action. A snapshot of these smaller galaxies being gently but inexorably pulled from their cosmic paths by the ghostly hand of friction. Are we witnessing the final stages of orbital decay for these satellites, destined to become the next meal for the cannibal giant? Or is their strange motion a clue to an even more complex gravitational history, a sign of past close encounters and near misses within the crowded cluster core? Each peculiar velocity is a data point in a billion-year story of attraction and resistance. Even the galaxy's magnetic personality is strangely subdued. Amidst the chaotic motion and violent history of the Coma Cluster, the vast space around NGC 4889 is threaded by a magnetic field that is unexpectedly calm and orderly. This is a profound cosmic contradiction. In such a turbulent environment, where galaxies collide and supersonic shock waves ripple through the hot gas, you would anticipate a magnetic field in total disarray, a tangled, amplified web of invisible force lines. Instead, the field measured here is relatively weak and shows a surprising degree of large-scale organization. How can such magnetic quiet persist in a place of such immense energy? The process that should be creating chaos is called turbulent dynamo amplification. Imagine stirring a cup of coffee with a spoon. The milk you add doesn't just sit there, it gets stretched, folded, and whipped into a complex swirling pattern. In the intracluster medium, the turbulent motion of the multimillion-degree gas should act like a cosmic spoon, stretching and amplifying the magnetic field lines, winding them into a tightly knotted and incredibly powerful structure. The fact that this hasn't happened, that the field remains so weak and ordered, means something must be actively suppressing this natural amplification. One possibility is that the very violence of the cluster's past has exhausted the turbulent energy on the largest scales. Perhaps the major mergers that built giants like NGC 4889 happened so long ago that the fiercest turbulence has had time to dissipate, leaving behind a smoother, more settled medium where only gentle, ordered motions remain. Another, more intriguing idea involves the scorching temperature of the gas itself. This plasma is so incredibly hot that the particles are almost completely ionized, meaning they are stripped of their electrons and move with tremendous freedom. In this state, the plasma might possess a very high magnetic resistivity, a property that makes it difficult for the magnetic field lines to be stretched and rearranged. It would be like trying to stir thick honey instead of water. The resistance to motion is far greater, preventing the turbulent dynamo from effectively winding up the field. This magnetic quiet is not just an absence of noise. It is an active state of suppression, a delicate balance of forces that allows order to emerge from a crucible of chaos. What does this serene magnetic field tell us about the ultimate fate of galaxy clusters? Does it suggest that even the most violent cosmic environments eventually settle into a long, quiet maturity, their inner turbulence spent, their magnetic whispers fading into a permanent hush. A subtle but profound timeline is written in the stars themselves. As you journey from the brilliant core of NGC 4889 out into its faint, extended halo, the average age of its stellar population gradually shifts. The very center is dominated by stars of immense antiquity, ancient suns that formed during the galaxy's earliest, most violent burst of creation over 10 billion years ago. This dense, ancient core represents the original seed, the primordial fragment from which the entire galactic titan eventually grew. Yet, as you move outward, the story changes. The stellar halo becomes a mosaic of ages, with distinct pockets of noticeably younger stars mixed in with the ancient population. This age gradient is not a flaw or an accident. It is a fossilized record of the galaxy's growth. The core tells the story of a rapid initial collapse, a furious period of star formation that used up the available gas and left behind a dense, old population. The outer regions, however, are an archive of later acquisitions. Each time NGC 4889 cannibalized a smaller galaxy, it didn't just add stars, it added that galaxy's entire star-forming history. A devoured dwarf galaxy that was still forming new stars right up until its destruction would contribute a fresh, youthful population to the halo, subtly lowering the average age in that specific region. The gradient is therefore a living timeline. The oldest stars at the center mark the beginning of the story, while the progressively younger stars in the outskirts chronicle a long and violent history of galactic feasts, each merger leaving its own distinct stellar generation as a permanent mark on the cannibal. Why doesn't the galaxy's immense gravity simply mix these populations into a uniform blend? The process of assimilation is surprisingly gentle on such vast scales. While the overall structure of a consumed galaxy is torn apart into streams, the individual stars are so far apart that they rarely collide. They are instead stirred into the halo, preserving the memory of their original birth date and chemical composition for billions of years. This stellar age map allows astronomers to read the biography of NGC 4889 not in words, but in the silent, burning testimony of its constituent suns. The galaxy's gravity carves mirages from the light of the ancient universe. Surrounding NGC 4889 and the entire Coma Cluster, astronomers observe breathtaking, crescent-shaped smears of light, the stretched and warped images of galaxies that lie billions of light years farther away. These are strong gravitational lensing arcs, cosmic illusions created when the combined mass of the cluster's stars, gas, and dark matter bends the fabric of space-time itself, acting like a flawed lens of unimaginable scale. The path of the distant light is curved as it travels through this warped space, forcing it to take a longer, bent journey toward our telescopes. The result is not just a simple magnification, but a profound distortion, turning pinprick galaxies into brilliant, elongated arcs that curve around the cluster's center. Each arc is a unique cosmic experiment, a precise measurement of gravity's strength at that specific location. By carefully mapping the shapes, lengths, and orientations of dozens of these arcs, scientists can perform a remarkable feat of cosmic cartography. They can trace the total distribution of mass within the cluster, creating a detailed profile of where matter, both seen and unseen, is concentrated. This is how we know with such certainty about the immense dark matter halo cocooning NGC 4889. The lensing arcs reveal that the visible stars and gas account for only a small fraction of the gravity required to create such extreme distortions. The rest, the dominant force sculpting these mirages, is the ghostly pull of dark matter. The pattern of the arcs is the dark matter's shadow, a perfect outline of its invisible presence. Some arcs are tight and close to the central galaxy, indicating a dense knot of mass right at its core. Others are wider and farther out, tracing the extended, diffuse halo that binds the entire cluster together. This gravitational map is so precise it can even reveal substructure, smaller clumps of dark matter associated with individual galaxies that have recently fallen into the cluster. It is the most direct evidence we have that dark matter is not a smooth, featureless cloud, but a complex, hierarchical scaffold upon which the visible universe is built. Why do some background galaxies appear as multiple mirrored images, while others are stretched into a perfect Einstein ring? The answer lies in the perfect alignment between the distant galaxy, the massive lens of the cluster, and our own line of sight. When the alignment is flawless, the light is bent in a complete circle, a rare and beautiful signature of a universe whose deepest laws are written in the language of geometry and light. These cosmic mirages are more than just pretty pictures. They are the universe's own scale, allowing us to weigh the invisible and map the intangible. This profound quiet extends to the very building blocks of creation. Astronomers have scanned the depths of NGC 4889 with our most sensitive instruments, hunting for the faint, cold signature of molecular hydrogen, the primary raw material from which new stars are born. They found almost nothing. It is a cosmic desert of staggering scale, a void where there should be bustling interstellar factories. This is not merely a shortage. It is a near total absence of the specific, dense, cold gas required to ignite a new generation of suns. Picture a vast, silent workshop, filled with all the tools and skilled craftsmen, but with no lumber or steel left to build anything new. This is the current state of this galactic giant. The lack of molecular gas poses a severe challenge because it defines the galaxy's ultimate fate. Without this fuel, star formation is impossible, locking NGC 4889 into its red and dead state permanently. How does a galaxy of such immense size and gravitational pull fail to retain or acquire this fundamental resource? The scorching heat of its multimillion-degree X-ray atmosphere provides one compelling answer. Any lingering clouds of cold molecular gas would be instantly evaporated, their delicate structures torn apart by the relentless bombardment of high-energy particles. It is like a delicate snowflake falling into a blast furnace, vanishing before it can even form a droplet. Another possibility is more final. The galaxy may have simply exhausted its entire reserve in a glorious, frenzied burst of star formation in the distant past, burning through its cosmic inheritance in a few billion years of spectacular creation. Every ounce of available gas was converted into stars, leaving behind the rich population we see today, but with nothing left in the bank for the future. Yet the most intriguing theory involves the galaxy's own past violence. The ancient quasar outbursts from the central black hole, and the relentless ram pressure from its motion through the cluster, may have acted like a cosmic broom, sweeping the entire system clean of this star-forming fuel. The galaxy's own turbulent history seems to have sterilized it, creating an environment so hostile that the delicate process of star birth can no longer take root. This extreme gas deficiency is the final piece of the puzzle, confirming that the galaxy's evolution has reached a terminal stage. It has transitioned from a vibrant, star-forming spiral into a quiet, elliptical relic, its days of creation now a billion years behind it. What does such a profound and permanent silence tell us about the ultimate fate of the universe's largest galaxies? This invisible rain of radiation is a testament to the galaxy's enduring power. While the central black hole now sleeps, its past eruptions and the ongoing violence of galactic mergers have filled the entire Coma Cluster with a faint, persistent glow of high-energy particles. These are cosmic rays, atomic nuclei stripped of their electrons and accelerated to nearly the speed of light, and gamma rays, the most energetic form of light in the universe. Detecting this specific signal from such a vast distance is like trying to hear a single whisper in a roaring hurricane. Yet its presence is a crucial piece of the cluster's energetic puzzle. How does a seemingly quiet galaxy manage to flood intergalactic space with such intense radiation? The answer lies in its history of unimaginable violence. During its active quasar phase, the supermassive black hole did not just inflate radio bubbles. It also acted as a natural particle accelerator. Its colossal jets, blasting out across millions of light years, would have generated immense shock waves within the hot cluster gas. These shocks are like cosmic surfboards, catching charged particles and riding them to incredible energies before flinging them out in the void. But the black hole is not the only engine at work. The relentless process of galactic cannibalism provides a second, more distributed source of power. Every time a smaller galaxy is torn apart and merged in the giant, the collision creates turbulence and colossal shock fronts within the intracluster medium. These chaotic flows continuously re-accelerate particles, giving them fresh boosts of energy long after the initial merger is complete. It is a cascade of violence, where the echoes of past cataclysms keep the particle background simmering. This high-energy haze is more than just a fossil. It is an active and dynamic component of the cluster's ecosystem. These particles contribute to the pressure that supports the cluster's atmosphere, and their relentless motion helps to keep the intracluster gas so intensely hot. They represent a hidden form of energy, a reservoir of power left over from the most violent chapters in the galaxy's life, still buzzing through the emptiness between the stars. What other invisible forces are at work, shaped by the fading echoes of this Titan's furious past? Wrapped around this galactic giant are the faint, ghostly ripples of a past impact. These are stellar shell structures, vast concentric arcs of stars that cascade through the outer halo like the rings left in a pond after a stone is thrown. They are the lingering echo of a galactic collision, a slow-motion crash that did not involve gas-rich spirals, but another ancient gas-poor giant. Astronomers call this a dry merger, a union of two red and dead galaxies that came together with no fuel left to spark new star formation. Without the chaotic turbulence of interstellar gas to disrupt the process, the event unfolded with a strange, clean precision. As the smaller galaxy was torn apart by the immense gravity of NGC 4889, its stars were not scattered randomly. Instead, they were slung out on vast, looping orbits, bunching up at the farthest points of their trajectory to create these sharp, shell-like overdensities. It is a gravitational miracle that these delicate structures have survived at all. In the crowded core of the Coma Cluster, you would expect the constant gravitational jostling from other galaxies to smear these ripples into a blur within a few 100 million years. Their continued presence, still crisp and distinct, is a cosmic clock. It tells us this specific merger was a relatively recent event in galactic terms, occurring within the last 1 or 2 billion years. This timeline transforms our understanding of the galaxy's life. It reveals that even a titan of such immense age and stability is not a finished product. Its growth through cannibalism did not end in the ancient past. but is an ongoing process, a continuous reshaping that continues to this day. The silent, rippled halo is a living fossil, a permanent monument to the last great collision that shaped this sleeping giant. The true weight of this galaxy holds a subtle but significant secret. Astronomers can measure the total mass of NGC 4889 by observing how fast its stars move, a technique that accounts for both visible stars and the pull of dark matter. They can also measure its total brightness, the combined light of all its shining suns. By comparing these two numbers, they calculate a value called the mass-to-light ratio, a fundamental way to understand what a galaxy is really made of. For a giant elliptical galaxy like this, composed mostly of old red stars, our models predict a specific expected ratio, but the measurements reveal a slight discrepancy, a quiet anomaly where the galaxy seems just a little bit heavier for its brightness than it ought to be. This tiny imbalance is a clue pointing toward three compelling possibilities, each one altering our view of the galaxy's inner makeup. The first theory suggests an unusual initial mass function. When this galaxy formed its stars billions of years ago, the process that dictates how many high mass versus low mass stars are born may have been skewed. Perhaps it forged a greater number of faint, low-mass red dwarfs than is typical. These dim stars contribute a huge amount of mass but very little light, acting like invisible anchors that increase the galaxy's weight without significantly boosting its glow. The second idea is that we are seeing the ghostly imprint of dark matter in an unexpected place. Our models assume dark matter is smoothly distributed in a vast halo. But what if a significant amount is concentrated within the visible body of the galaxy itself, intricately mixed with the stars? This would add gravitational weight right where the starlight is, boosting the mass-to-light ratio in a way that a simple halo cannot explain. The final possibility is that the galaxy's violent history has left behind a hidden graveyard. Countless stellar corpses, like white dwarfs, neutron stars, and black holes, the faded remnants of massive stars that lived fast and died long ago, could be lurking unseen within the stellar population. These dark remnants are heavy but emit almost no light, subtly shifting the ratio. This anomaly forces a deeper question. Are the universal rules for star formation less rigid than we thought, able to produce different stellar recipes in different cosmic environments? Or does this slight imbalance reveal a more intimate and complex relationship between dark matter and the stars it guides? The answer is written in the faint, missing light of this colossal galaxy, a small number that hints at a universe of hidden structures. A faint, unresolved fog of X-rays clings to the galaxy, an emission that simply cannot be explained by adding up all its known power sources. We have already counted the brilliant ultra-luminous X-ray sources and the scorching atmosphere, but when we subtract their known glow, a persistent, diffuse background remains. It is a cosmic static, a whisper of high-energy light with no clear origin. One compelling possibility points to a hidden multitude, a vast population of faint binary star systems where a white dwarf or neutron star is steadily siphoning material from a companion. Each one is too dim to see individually across this immense distance, but their combined emission could create this pervasive, unresolved haze. It would be like listening to a vast stadium crowd from a mile away. You cannot pick out any single voice, but the collective roar is unmistakable. Yet an even more profound explanation whispers from the edges of physics. This faint X-ray glow could be the signature of dark matter itself. Certain theoretical models suggest that dark matter particles are not completely stable, that they can occasionally decay or annihilate each other, transforming their mass into energy and releasing a faint spray of X-rays in the process. If this is true, then the unresolved background around NGC 4889 is not a mere collection of stars, but the ghostly radiance of the universe's most mysterious substance slowly fading away. This would mean we are not just mapping the dark matter halo through gravity, but are potentially seeing its faint, intrinsic glow for the very first time. Why would this signal be stronger here than in other galaxies? The answer may lie in the galaxy's incredible density. Its immense dark matter halo, shaped by countless mergers, could provide the perfect crowded environment for these rare particle interactions to occur more frequently. We are left with two vastly different universes, one filled with countless unseen stellar corpses, and another where the fabric of reality itself is subtly luminous, which is the true source of this faint, high-energy sigh. Deep within the galaxy's ancient heart, a separate stellar city spins in secret. The central core of NGC 4889 is not moving as a single, unified whole. While the vast majority of the galaxy's stars orbit in one general direction, the innermost stars march to the beat of a different cosmic drum, rotating on a completely separate plane or with a distinct velocity. This is a kinematically decoupled core, a fossilized imprint of a galactic collision so monumental it left a ghost spinning inside the victor. Imagine two massive whirlpools in an ocean, each with its own strong circular current, colliding and merging. The outer waters of the smaller whirlpool would be stripped away and absorbed, but its innermost, most tightly wound vortex could survive intact, continuing to spin within the new, larger body of water. This is precisely what happened to NGC 4889. During a colossal merger with another large galaxy billions of years ago, the outer stars of the victim were torn away and assimilated into the halo, creating the stellar streams and the chaotic orbits we see today. But the dense, tightly bound core of that galaxy, where stars are packed together millions of times more densely than in our own neighborhood, possessed enough gravitational self-control to resist being completely shredded. It survived the violent encounter largely intact, plunging straight into the heart of NGC 4889 and settling at its center. Now, this captured nucleus continues its ancient dance, a permanent reminder of the galaxy that was consumed. Its distinct motion is not just a curiosity, it is a direct measurement of that long-ago impact. The angle of its rotation reveals the trajectory of the collision, while its speed hints at the mass of the galaxy that was devoured. This decoupled core is more than a relic. It is a celestial matryoshka doll, a galaxy within a galaxy, holding the identity of a separate universe that ceased to exist eons ago. What other lost histories might be preserved in the silent, independent spin of these captured suns? A faint, pervasive light haunts the spaces between the stars of this ancient galaxy. This is the diffuse ionized gas, a sea of superheated plasma so thin and spread out it defies the very silence that surrounds it. We can detect it not by its own glow, but through the specific, ghostly fingerprints it leaves in the spectrum of light, certain emission lines that reveal its presence. The gas is ionized, meaning its atoms have been stripped of their electrons, and to maintain that state requires a constant source of energy, a relentless barrage of radiation to keep it hot. This is the core of the mystery. NGC 4889 is a red and dead galaxy, a place that has not formed new, massive stars for billions of years. Those young, brilliant stars are the universe's most efficient ionizing engines, and without them, the gas should have cooled down long ago, its electrons recombining with their atoms to form a cold, dark, and neutral fog. Yet the glow persists, So what cosmic power source is still humming, still pumping energy into this galactic atmosphere eons after the fires of stellar birth have gone out? One suspect is the galaxy's vast population of old, dying stars. While they are not the brilliant ultraviolet beacons that young stars are, their collective, faint output could provide a steady, low-level trickle of ionizing radiation. It would be like heating a vast room with a million dying embers instead of a single roaring fire. Another possibility points to the past fury of the central black hole. The radiation from its ancient quasar phase, though the outbursts ended millions of years ago, may have been so intense that it left the gas permanently ionized, a fossilized state that has simply never had the chance to cool down. Or the heat could be external, bleeding in from the scorching multimillion-degree plasma of the intracluster medium that envelops the entire galaxy. This would be like a planet being warmed by its star, but on a galactic scale, with the cluster itself acting as a colossal radiator. The true answer likely involves a combination of these sources, a layered history of energy deposition that has left this gas in a permanent state of excitement. This faint, glowing sea is a thermal echo, a reminder that even in a galaxy that appears to have reached its end, energetic processes continue to thrum just beneath the surface, powered by the fading echoes of its violent past. How many other silent giants are similarly cloaked in this faint, warm breath, their final state of rest perpetually delayed by the ghosts of their own history? Measuring a galaxy's motion across the sky is a task of almost laughable difficulty. The proper motion of NGC 4889, its tiny, actual shift in position relative to the distant cosmic backdrop, would be smaller than the width of a human hair seen from a mile away. We are attempting to track the drift of a city of stars from over 300 million light-years away. Yet, if our instruments could ever achieve such impossible precision, the reward would be a key to unlocking the Coma Cluster's deepest secrets. This minuscule measurement is not just about the galaxy's speed. It is a direct window into the invisible gravitational forces that bind the entire cluster together. By plotting its precise path, we could trace the orbit of this Titan as it swings around the cluster's center of mass. That orbital path is a cosmic speedometer, telling us exactly how fast it is moving and, by extension, how much total mass, including all the dark matter, must be present to keep it from flying off into space. We could weigh the entire cluster with a single, perfect measurement. The dynamics revealed would be breathtaking. Is NGC 4889 on a slow, circular cruise, a sign of a relaxed and settled cluster? Or is it on a highly eccentric plunge, screaming through the core on a chaotic trajectory that speaks of a recent and violent merger? Its proper motion would tell us. It would reveal the galaxy's ultimate fate, showing whether it is destined to settle near the cluster's heart, or if it will swing back out into the distant halo. Every subtle tug and pull on its path would map the hidden lumps and threads of dark matter, the cosmic scaffold that guides its journey. For now, this measurement remains a tantalizing future goal, a whisper of data just beyond our grasp, promising that one day we might not just see this giant, but watch it move. These faint stellar tendrils are the final breaths of dying galaxies. Wrapped around NGC 4889 are the ghostly remains of its smallest victims, dwarf satellite galaxies caught in a gravitational death spiral. As they swing too close to the Titan, its immense pull stretches them into long, thin rivers of stars, creating delicate tidal tails that stream away into the darkness. This is not a slow, gentle process, but a violent, real-time dissection happening right before our eyes. These tidal tails are a cosmic laboratory, letting us watch the fundamental physics of galactic destruction unfold on a human timescale, a rare window into the final moments of a galaxy's life. Imagine a ball of cotton candy pulled apart by two strong hands, its sugary strands stretching into thin, wispy threads before they finally snap. This is what gravity is doing to these dwarfs, but on a scale so vast it defies comprehension. The precise shape and length of each tail tells a specific story. A long, thin, and relatively straight tail indicates a recent, fast, and brutal encounter, a single, devastating pass that sent stars flying. A tail that is shorter, broader, or shows subtle curves and kinks suggests a slower, more drawn-out process, perhaps the galaxy's final orbits as it was gradually shredded over millions of years. By mapping these structures, astronomers can rewind the cosmic clock, calculating the exact trajectory and speed of the initial encounter. They can determine the dwarf galaxy's original mass and even the density of its dark matter halo, a property that is otherwise nearly impossible to measure directly. The very existence of these distinct tails, which have not yet dissolved into the main halo, reveals the limits of a small galaxy's survival. They show us the precise point at which a galaxy's own gravity can no longer hold it together against the overwhelming tidal forces of a giant. Each wisp of stars is a silent testament to a battle already lost, a beautiful and tragic signature of the relentless power that shapes our universe. What does the final snap of a galaxy sound like in the silent void of space? A final, subtle clue is written in the simple relationship between color and brightness. For the vast populations of stars and globular clusters within giant galaxies, a fundamental rule usually holds true: the color-magnitude relation. Brighter, more massive stars burn through their fuel quickly and glow with a hotter, bluer light, while fainter, lower-mass stars are cooler and redder, living far longer. This creates a predictable pattern, a tight sequence where brightness and color are neatly correlated, like a well-organized line of people sorted perfectly by height. In NGC 4889, however, this line is not neat and orderly. It is a scattered crowd. The relationship between the color and brightness of its countless stars and clusters shows an unusually large amount of scatter, a chaotic spread that breaks the expected pattern. Some bright objects are surprisingly red, while some faint ones are unexpectedly blue. This scatter is far more than a simple statistical fluctuation. It is a direct signature of the galaxy's violent and diverse assembly. Each point of light that breaks the line is a refugee from a different homeland. Imagine taking the populations from a dozen distinct cities, each with its own unique demographic history, and mixing them into one vast metropolis. The overall pattern of age and wealth would no longer be smooth and predictable, but would show pockets and outliers reflecting the different origins of the people. This is what has happened to the stars of NGC 4889. The chaotic scatter in its color-magnitude relation means its stars did not all form together from a single, well-mixed cloud of gas. They were forged in many different galactic cauldrons, each with its own star-forming history and chemical enrichment. A cluster of stars that is too red for its brightness might have formed in the core of a large, mature galaxy that had already created multiple generations of metal-rich stars. A star that is too blue for its faintness could be an ancient, pristine sun from a primitive dwarf galaxy that was consumed before it could enrich its gas. The galaxy's immense gravity has stirred these populations together, but it has not blended them into a uniform soup. Their distinct birthplaces are permanently recorded in this scattered diagram, a graph that is less a clean line and more a messy fingerprint of countless mergers. This heightened scatter sets NGC 4889 apart from other giant ellipticals that may have had a more peaceful internal evolution. Its chaotic assembly history is not just a story told by streams and shells, but is encoded in the very light of its most fundamental constituents. Why does this specific pattern of chaos persist after billions of years? It reveals that the galaxy's growth was not a single event, but a long and messy process of accumulation, leaving behind a stellar population as diverse and complex as the history that created it. Even the very light emitted by this galaxy holds a secret signature we cannot decipher. Scattered throughout its spectrum are faint, unidentified emission lines, sharp spikes of energy at specific wavelengths that stubbornly refuse to match the fingerprint of any known atom or molecule in our entire periodic table. It is as if we are listening to a cosmic symphony and hearing notes that do not belong to any known scale. These are not random blips or noise. They are precise, repeatable signals, which means they must be coming from a real physical process happening within the galaxy. The immediate suspicion, of course, falls upon our own technology. Could these be subtle instrumental artifacts, ghosts in the machine created by the complex optics of our telescopes or the sensitive electronics of our spectrographs? Yet, the lines appear consistently across different observational campaigns and sometimes in other galaxies within the cluster, which makes a simple equipment error far less likely. This points toward a genuine astrophysical origin, something happening out there in the depths of space that we have not yet witnessed or understood. One compelling possibility involves exotic states of matter under conditions we cannot replicate on Earth. Imagine a form of plasma so hot and dense that atoms are stripped down to their bare nuclei and electrons behave as a single, collective fluid. In such an extreme environment, the rules of atomic physics can change, potentially permitting forbidden transitions that produce light at wavelengths we have never before cataloged. Another, more speculative idea reaches into the realm of dark matter. Could certain theoretical dark matter particles, like actions or other weakly interacting slim particles, decay or annihilate and release their energy as a faint, specific photon? This would mean the unidentified lines are not a signature of normal matter at all, but the direct, long-sought glow of the universe's most elusive substance. Alternatively, the answer might lie in complex molecular compounds we have not yet considered, vast clouds of exotic ices or dust grains with unique crystalline structures that can emit or fluoresce in strange and unpredictable ways when bathed in the galaxy's ambient starlight. Each of these possibilities opens a door to a radically different understanding of cosmic chemistry and physics. The persistence of these unknown lines is a stark reminder of the limits of our knowledge. Our maps of the atomic universe are still incomplete, and the greatest discoveries often begin with a single, unidentifiable whisper from the dark. What other fundamental ingredients of reality might be hiding within these spectral mysteries, waiting for the key that will unlock their true nature? Another invisible breath seems to warm the galaxy's dark spaces. At the far end of the electromagnetic spectrum, in the realm of submillimeter wavelengths, astronomers have detected a faint but persistent glow that simply should not be there. This is the submillimeter excess, a subtle yet undeniable surplus of radiation that our best models of cosmic dust completely fail to predict. We thought we understood the galaxy's thermal signature, the predictable way dust grains of various sizes absorb starlight and re-emit it as heat. But this extra light is a ghost in the machine, a whisper of energy with no clear origin. So what is producing this unexpected warmth? The first and most straightforward suspect is a hidden population of dust, but not the kind we are familiar with. This would be an immense reservoir of profoundly cold dust, grains chilled to just a few degrees above absolute zero. At such frigid temperatures, these particles would emit almost all of their radiation in this exact submillimeter band, effectively hiding in plain sight. The existence of this cold dust would itself be a major puzzle. How could it remain so deeply frozen while suspended in a galaxy enveloped by a multimillion degree X-ray atmosphere? It would require incredibly dense, shielded pockets where the intense heat from the surrounding gas cannot penetrate, like finding blocks of ice preserved deep within a volcano. Another possibility challenges our very understanding of the dust grains themselves. Perhaps the problem isn't the temperature, but the texture. What if the dust in NGC 4889 isn't made of smooth, spherical particles, but is instead a tangled fog of fluffy, porous aggregates? These complex structures, more like microscopic snowflakes than tiny stones, would have wildly different thermal properties. Their intricate shapes could absorb and re-radiate energy far more efficiently at these long wavelengths, creating the observed excess glow without requiring impossibly low temperatures. This would mean the interstellar debris in this ancient galaxy has a unique and alien composition, sculpted by its violent history in ways we are only beginning to imagine. The most thrilling possibility, however, is that we are seeing the signature of an entirely new physical process. This faint submillimeter signal could be the first hint of a quantum phenomenon occurring within the dust clouds themselves, or perhaps even a subtle energy release from the decay of dark matter particles. Each explanation opens a door to a different universe. Is the galaxy veiled in a shroud of impossible frost? Is it filled with dust of an unimaginable shape? Or is it humming with a physics we have yet to name? This faint excess is more than a measurement error. It is a quiet call from the darkness, reminding us that even the coldest, most forgotten corners of a dead galaxy can still hold the seeds of discovery. The galaxy's faintest ghosts are the dying embers of its first suns. Scattered throughout the vast halo of NGC 4889 is a silent, hidden multitude of white dwarfs, the Earth-sized cores of stars that have long since burned through their nuclear fuel. Each one is a fading cinder, a cosmic tombstone for a star that once shone brightly. These stellar remnants are so incredibly dim that spotting them individually across such a colossal distance is like trying to see a single candle flickering on the moon. They exist just at the edge of our observational capabilities, their collective light blending into a faint, unresolved fog that permeates the galactic outskirts. Yet their suspected numbers are staggering, potentially accounting for a significant fraction of the halo's very oldest stellar population. This hidden census holds the key to the galaxy's deepest past. The total number and distribution of these white dwarfs would act as a precise clock, constraining the timeline of the galaxy's very first, most violent burst of star formation. If the models are correct, and the halo is indeed swarming with these ancient remnants, it would mean that the primordial version of NGC 4889 experienced a ferocious and incredibly efficient period of creation, forging vast numbers of stars in a relatively short cosmic time. The sheer abundance of these white dwarfs would be the final, fading evidence of that initial frenzy. But if the numbers are lower than expected, it would force a dramatic rewrite of the galaxy's origin story. It could mean the earliest star formation was a more drawn-out and less productive process, or that the halo was built more gradually from the cannibalization of many small, primitive galaxies that themselves had very different star-forming histories. How many of these faint embers must there be to account for the gravity we measure? Their silent, invisible presence is a direct challenge to our theories, a ghostly population whose faint light, if we could ever truly see it, would illuminate the very first chapter in the life of this cosmic titan. This sleeping giant has left its handwriting all over the galaxy. The radial lobes, the X-ray cavities, the scorching gas, and the profound lack of star formation are not separate mysteries. They are different chapters of the same story, a cycle of self-regulation known as Aegean feedback. It is the tale of how the central black hole, in its violent feasting, ultimately built the prison that holds it today. The cycle begins quietly, with cold gas gradually flowing toward the galactic center, drawn in by the immense gravity. This gas is the lifeblood for new stars, but it is also the only food that can wake the slumbering monster. As this fuel spirals inward, it forms a vast, swirling accretion disk around the black hole, heating to incredible temperatures and unleashing a blaze of radiation. The black hole has awoken, transforming into a brilliant quasar. But this awakening is not a gentle process. A portion of the infalling material is channeled and focused into two opposing relativistic jets that blast outward from the poles at nearly the speed of light. These jets act as cosmic blowtorches, drilling through the galaxy's gaseous halo. They inflate the colossal radial lobes, pushing the hot X-ray emitting gas aside to carve out the vast cavities we still observe millions of years later. This is the feedback loop in its most destructive phase. The energy from the jets and the intense radiation heats the surrounding gas to millions of degrees, making it so hot and turbulent that it can no longer collapse to form new stars. The black hole's outburst effectively sterilizes its own galaxy, shutting down the very nurseries that might have provided it with future meals. It is a dramatic act of self-sabotage. Over time, this heated gas expands outward, pushing potential fuel far away from the galactic core. With its food supply cut off, the black hole's accretion disk starves, the jets sputter and die, and the quasar fades back into silence. The monster returns to its dormant state, surrounded by a hot, inhospitable atmosphere of its own creation. The cycle is complete, but it is not a one-time event. The fossil bubbles at different distances from the core tell us this has happened repeatedly. Each time a new trickle of gas managed to find its way inward, the beast would stir, unleash a new outburst, and reheat its environment, maintaining the galactic desert. This feedback cycle is the ultimate explanation for the galaxy's red and dead state. It is why we see no cold gas for star formation, and why the black hole now sleeps in profound quiet. The monster is not dormant because it is weak, but because it was too powerful for its own good, sculpting its entire galaxy into a monument to its own past fury. How many times did this cycle of awakening and slumber play out before the galaxy finally ran out of fuel for good? The relentless pull of this cosmic giant does more than just tear galaxies apart. It also fundamentally reshapes the survivors. Orbiting satellites endure a constant, rhythmic gravitational stress from NGC 4889, a process known as tidal heating. Each time a smaller galaxy swings close on its elliptical path, the difference in gravity between the side facing the giant and the side facing away gives it a sustained and vigorous shake. This is not a single catastrophic event, but a cumulative billion-year workout that steadily injects energy into the satellite's stellar population. Imagine holding a bag of marbles and shaking it gently but persistently. The marbles will not instantly fly out, but they will slowly begin to shift and spread, causing the entire bag to puff up and become less dense. This is precisely what happens to a satellite galaxy. Its stars, once orbiting in a compact and orderly disk or sphere, have their orbits energized and enlarged. The entire galaxy inflates, becoming more diffuse and extended over cosmic time. This subtle transformation is a powerful forensic tool. The degree of puffiness, the amount by which a satellite galaxy has been inflated, is a direct measure of the gravitational force it has endured across its entire orbital history. By mapping the stellar distributions of many satellites at different distances, astronomers can perform a remarkable feat of reverse engineering. They can calculate the strength and reach of the tidal forces that cause the heating. And since those forces are generated by the total mass of NGC 4889, including its vast dark matter halo, this provides a unique method to weigh the invisible giant. The results are profound. The pattern of tidal heating reveals not just the halo's total mass, but its shape and density profile. Is the dark matter packed tightly toward the center, or is it spread more evenly throughout a vast volume? The way the satellites are puffed up provides the answer. A satellite that has endured intense heating tells us it has ventured through a region of incredibly strong gravity, pointing to a dense, cuspy core of dark matter. Another, orbiting farther out but still showing signs of inflation, helps trace the halo's gradual thinning at its edges. This method acts as a cosmic scale, using the visible damage to the satellites to measure the unseen mass of the predator. Why do some satellites appear more puffed up than others? Their individual survival stories, the specific paths they have woven around the cannibal, are written in their inflated stellar halos. Each one is a living gauge, its distorted form a permanent record of the immense, ghostly presence that surrounds them. Deep within the immense gravitational well of this galaxy, time itself begins to falter. The sheer concentration of mass, from its billions of stars to its colossal dark matter halo, warps the fabric of space-time so profoundly that it tugs on the very flow of time. For a hypothetical observer braving the void near NGC 4889, clocks would tick just a fraction of a second slower than for someone watching from the distant, undisturbed emptiness of intergalactic space. This is not science fiction. It is a direct prediction of Einstein's theory of general relativity, a phenomenon called gravitational time dilation. The effect is incredibly subtle, far too small for any human to ever perceive, yet it is undeniably real. It is as if the galaxy sits in a valley of time, where the steep gravitational slopes cause the river of time to flow more slowly than on the flat plains far away. This cosmic slowdown must be accounted for in our most precise observations. When astronomers measure the flicker of distant quasars or the regular pulses from pulsars located behind the galaxy, the path their light takes is bent and slowed by this warped space-time. If we did not correct for this relativistic delay, our cosmic maps would develop tiny, cumulative errors, like a clock that slowly falls behind over centuries. The immense quiet of this giant is therefore an illusion in more ways than one. Beneath the calm exterior, the galaxy is a dynamic engine of relativity, actively bending light and stretching time with its silent, invisible weight. What other subtle distortions might this titan be imprinting upon the light that passes it by? And what secrets about gravity itself are encoded in those faint, temporal whispers? These final breaths of stars are not confined to the galaxy that birthed them. Drifting in the absolute emptiness between galaxies, far from any spiral arm or stellar nursery, are the solitary ghosts known as intracluster planetary nebulae. They are the dying size of stars that were violently ejected from their galactic homes, now floating as isolated beacons in the intergalactic dark. Each one is a testament to a stellar life lived in profound solitude, a sun that spent its final millennia utterly alone. How does a star end its days so far from any galaxy? The same gravitational turmoil that creates the vast streams of tidal debris also flings individual stars out into the void. When a small galaxy is torn apart by NGC 4889, the chaotic gravitational forces don't just pull stars into streams. They can also act as a slingshot, launching stars on trajectories so fast they escape the galaxy entirely. These stellar runaways carry on through the cluster, living out their lives in isolation until, in their final act, they puff off their outer layers. Without a galaxy's ambient light to wash them out, these isolated planetary nebulae become incredibly valuable tools. They act as single, bright points of light, perfect tracers for the faint, diffuse sea of intracluster light that is otherwise too dim to study in detail. By counting these objects and plotting their positions around NGC 4889, astronomers can create a three-dimensional map of the ghostly stellar debris that the cannibal galaxy has shed over billions of years. It is like finding a handful of brilliant diamonds scattered across a dark, vast beach, each one illuminating the contours of the hidden sand beneath. Their distribution is not random. They trace out the faint plumes and shells that are the echoes of specific galactic collisions. The very presence of these intracluster planetary nebulae confirms that a significant portion of the stars torn loose during mergers do not fall back into the giant, but become permanent nomads, their final glowing shrouds marking the true, invisible extent of the carnivore's influence. What does it feel like to be a star that dies in the absolute silence between galaxies, its last beautiful gasp witnessed by no one but the endless dark? This galaxy acts as a colossal, hidden particle accelerator. The high-energy cosmic rays generated by its past fury now travel through the cluster, but their journey is far from a straight shot into the void. They must navigate the vast, magnetized maze of the intracluster medium, a thin but incredibly hot plasma threaded by invisible magnetic fields. This magnetic environment is the key to the mystery, transforming the propagation of these particles from a simple flight into a chaotic, random walk. A single cosmic ray, a proton or atomic nucleus moving at nearly the light speed, does not travel in a clean line. It is constantly forced into a spiral path, corkscrewing around the weak but pervasive magnetic field lines that fill the space between galaxies. Each tiny deflection adds up, causing the particle to diffuse outward in a slow, meandering drift rather than a rapid escape. The central question is how long these particles remain trapped within the cluster's gravitational and magnetic grasp. Their confinement timescale is a critical piece of the cosmic puzzle. If they diffuse away quickly, their energy is lost to the vast intergalactic space, doing little to influence the cluster's internal dynamics. But if they are confined for hundreds of millions of years, they become a persistent, buzzing energy source, contributing significantly to the pressure that keeps the intracluster medium so hot and inflated. This lingering energy reservoir helps explain why the gas between galaxies does not simply cool, collapse, and form new stars in a dramatic renaissance. The cosmic rays provide a form of indirect heating, a steady background hum that maintains the galactic desert. The exact duration of their confinement depends on the strength and tangled structure of the magnetic fields, properties we are still struggling to measure. Are these fields a tightly knotted web that traps particles efficiently, or a looser, more open structure that allows them to leak away? The answer determines the entire energy budget of the cluster, revealing whether the ghostly breath of past explosions is enough to shape its present and future. How many other silent giants are similarly sustained by the fading echoes of their own violence, their energy captured and recycled by invisible magnetic cages? Its long orbital dance will eventually draw it into a final, breathtaking collision. NGC 4889 and its colossal neighbor, NGC 48874, are not static giants, but two titans locked in a slow gravitational embrace, circling the heart of the Coma Cluster. Over timescales that dwarf human history, their mutual attraction will inexorably pull them closer, setting the stage for the most spectacular merger the local universe has seen in billions of years. This is not the cannibalism of a small satellite, but the ultimate union of two galactic superpowers. The process is governed by the same dynamical friction we glimpsed with the smaller satellites, but on an unimaginably grander scale. As each galaxy moves through the other's extended dark matter halo, they create immense gravitational wakes that act as a cosmic brake, steadily sapping their orbital energy. Their vast, diffuse halos of stars will be the first to touch, intertwining like two clouds of smoke long before the galactic cores make their final, fateful approach. When the central cores do finally meet, they will not collide head-on like billiard balls, but will swing past each other in a series of close, dramatic passes. With each pass, the tidal forces will be catastrophic, pulling colossal streams of stars from each galaxy and hurling them into the intergalactic void. The supermassive black holes at their hearts will also begin their own dance, sinking toward the new common center of mass through this same dynamical friction. After a billion-year ballet of chaos, they will form a tight binary system, orbiting each other at a fraction of a light year, before their own final merger unleashes a tsunami of gravitational waves across the cosmos. The resulting entity will be a single, almost incomprehensibly large elliptical galaxy, a behemoth that could be the final dominant structure in the cluster's core for the rest of cosmic time. This future giant will be the ultimate red and dead galaxy, having long ago exhausted every last wisp of its gas reserves, its stellar population aging in unison toward a permanent dark silence. Will this be the final form of structure in this region of the universe, a solitary monarch ruling over a graveyard of consumed galaxies? Our journey through these 50 phenomena inevitably circles back to a single, profound coincidence: our own existence as observers. We are here on a pale blue dot, deciphering the secrets of a giant 300 million light-years away. This is not a trivial fact. It is a fundamental part of the mystery itself. The universe is precisely old enough for titans like NGC 4889 to have lived their violent lives, to have cannibalized their neighbors, and for their black holes to have fallen into a deep slumber. Yet it is also young enough that their light has had time to travel across the cosmic void and into the lenses of our telescopes. We occupy a narrow, privileged sliver of cosmic time, a golden window where the universe has grown complex enough to produce galaxies, planets, and life, but has not yet expanded into an eternal, dark silence where such structures are too distant and faint to ever see. Every strange phenomenon we have explored, from the silent black hole to the ghostly stellar streams, is a story we are able to read only because of this fragile alignment. The very laws of physics that allow galaxies to form also permit the chemistry of life to emerge. The same force of gravity that sculpts those colossal radial lobes also holds our world in orbit around its star. This is the anthropic principle in its most breathtaking form. A simple acknowledgement that our ability to ask these questions is inextricably linked to a universe capable of producing the answers. We are not merely external spectators. We are a product of the same cosmic processes that built the giant we study. The iron in our blood was forged in the heart of a long-dead star, a star that may have once belonged to a galaxy consumed by a cannibal like NGC 4889. Our contemplation is the universe becoming conscious of itself. So as we conclude this catalog of wonders, the final and perhaps greatest mystery is not one of the galaxy's 50 phenomena, but the astonishing fact that we are here to count them at all. What other cosmic coincidences have aligned to grant us this front row seat to the grandest show in the universe? 50 separate mysteries have painted a single, breathtaking portrait. NGC 4889 is not a frozen relic in the cosmos, but a living, breathing ecosystem on a scale we are only beginning to comprehend. Its silent black hole, its cannibalized streams, and its ghostly dark matter halo are not isolated oddities. They are interconnected threads in the grand tapestry of galactic life and death. Every strange phenomenon we have explored, from the frantic dance of core stars to the faint whisper of unidentified light, is a vital piece of the puzzle, revealing how the universe's largest structures are built, how they thrive, and how they eventually grow quiet. This giant teaches us that a galaxy is not merely a collection of stars, but a dynamic history book, its pages written in the motions of captured clusters, the chemistry of stolen suns, and the fading echoes of its own violent past. The next time you find yourself beneath a clear night sky, look up. Let your gaze drift toward the constellation of Coma Baronesses, and know that within that darkness rests a titan whose story is still being written. Its 50 secrets have reshaped our understanding, but countless more are waiting to be found. What cosmic mystery captures your imagination the most? Share your own favorite enigma of the deep universe in the comments below, and keep looking up with wonder. Solving these 50 mysteries will require a new generation of eyes on the cosmos. The James Webb Space Telescope, with its unparalleled infrared vision, is perfectly poised to peel back the layers of this giant. It could stare straight through the galaxy's dusty veils, hunting for those faint, cold pockets of molecular gas that have so far eluded detection, finally answering whether any star-forming fuel remains hidden in its depths. Webb's spectrographs might also decode the unidentified emission lines haunting the galaxy's spectrum, determining if they are the signature of exotic molecules or something far more profound. Meanwhile, the Vera-C Rubin Observatory will conduct its own form of cosmic surveillance. Its relentless, decade-long survey of the entire sky will watch for the brief, brilliant flare of a tidal disruption event, that rare moment when a star is torn apart by the central black hole, giving us a direct and dynamic measurement of the sleeping monster's appetite. Rubin's wide field view will also map the faintest stellar streams and shells with unprecedented clarity, turning the subtle whispers of past mergers into a shouting, detailed history of the galaxy's violent growth. These observatories do not just represent better technology, they are gateways to a new era of understanding. They will transform NGC 4889 from a collection of static, puzzling images into a dynamic story we can watch unfold across time. The next great discovery about this cosmic titan is not a matter of if, but when, waiting for the right instrument to turn its gaze toward the darkness and finally hear the galaxy's secrets. Spoken in wavelengths of light, we are only just learning to